What's strange about this circuit is that we have an inverting op-amp configuration, but we also have a positive feedback loop here. So how do we face this? Well, I will do what I know, and I will name this node X, alright? I will say that there is a current flowing from the input voltage all the way to here and then goes up here because it can't really flow inside the inputs of the op-amp. I would say that some of the current might flow inside the op-amp or outside from it, and some of it will flow downwards here. I will call this node N, this node at the input of the op-amp. Alright, I didn't do anything special up until now. I did things from generic methodology that I would normally do. Well, if I perform Ohm's law on the resistance R1, I'll get that R1 is Vin minus Vx over the common current I. Again, for the resistor R2, I'll do the same, Vx minus, how much here? V out over I, the common current. And if I said that this current is the same as this current, therefore I can solve in respect to Vx and get this result. Now I can eliminate Vx from any equations that will come up in the future. I noticed that from here all the way to here is a common voltage divider. Well, because it's a common voltage divider, I know that the voltage at Vn must be equal to R4 over R3 plus R4 times V out. Now, I know that for an ideal op-amp, this equation must hold true whenever I have a negative feedback configuration. I have a negative feedback configuration. I also have something strange here, but I don't pay attention to it. And I'm not sure if I'm going to say that Vx it must be equal to Vn, all right? Because this would be true in a negative feedback configuration. But now I'm not sure what's going to happen. So I'll write this general equation here and I will see how things go. Well, if I replace V plus, which is here, with Vn, and V minus with Vx, alright, these are the same voltages, and I replace Vx from here and Vn from here, I get this amazing result over here. Alright, take some time to digest this, and what I'm going to do is I am going to make some observations. Well, first and foremost, I'll say that what if A0 is infinite? Alright, we're talking about an ideal op-amp here. What if it's infinite? Well, to avoid saturation, we want this denominator to not become 0. So R2 over R1 must be not equal to R3 over R4. What if they have been equal, or what if they have been very close? Well, if they were very close or equal, our output would be huge. If you had very large swings at the output, that would not be really under our control. The op-amp would be saturated. It would not be very useful. Our configuration would be useless. So we must avoid this, or this more general, alright, if we had more finite gain here. And what I'm going to do is I'm going to write again my equation here, and I'll say, well, what if the gain was infinite? And what if R3 was also infinite? Alright, what if R3 was infinite? That would mean that this would be an open circuit here, alright? which would mean that I would predict that I would have a normal inverting op-amp configuration here with the positive terminal connected all the way to the ground. Since I expect no current to flow inside the positive terminal, this resistor would play no role in the result. And indeed, if I do the math here, I get that V out over V in must be equal to minus R2 over R1. And this is huge. This says to me that if this resistor was very, very large, this would simulate a typical inverting op-amp, so my result is probably correct. Yes, this is a typical inverting op-amp configuration. And what if now I go and say that, well, if the gain was infinite, I would notice this behavior. I would notice two behaviors. Well, if I know that R3 over R4 and R2 over R1 are not equal, if I made sure they were not equal, and I say that if this was lower than this, I would notice a non-inverting behavior. I'll notice that V out would be positive in respect to V in. Alright, you can see it here. This denominator would be positive, and my output would be positive if I had the positive inputs. Respectively, if R3 over R4 was larger than R2 over R1, I would notice an inverting behavior from my results. This says to me, again, I have two very, very different behaviors. Three, if you count that there is a case where R3 over R4 is very close to R2 over R1. And that's it. This is the very strange configuration. We must, of course, be careful when we have positive feedbacks to avoid saturation. Well, I was very careful to do things that I knew were correct. And I also noticed that there was also a negative feedback. If I didn't have a negative feedback and I had only positive feedback, well, I couldn't really do the same things I did here. I would have something resembling an oscillator, so my configuration would work much, much more differently. Now you know how to attack similar circuits. Study well and take care.